Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. In the last episode we examined the connection between process efficiency and entropy generation, and found that for a heat engine we could directly link entropy generation in specific steps of the cycle to loss of work output. In the case of a closed system Stirling cycle, this entropy generation could be traced to temperature gradients that exist at various points in the cycle, allowing us to better understand the root cause of this inefficiency. However, this was for a closed system heat engine. How do we generalize these basic ideas to open system processes that involve mass flows, reactions, or multiple work or heat flows? That brings us to today's cartoon, which went viral on the internet a few years ago in the context of equity in education. A group of animals are lined up awaiting some kind of selection process, which, as they suddenly find out, is determined by their ability to climb a tree. This is certainly a quantitative, measurable benchmark, but is it a fair assessment of their relative worth as an animal? The same is true for process efficiency. Many textbooks in thermodynamics introduce the concept of Carnot efficiency as if it were some kind of universal scale on which to judge all energy conversion processes. But is it? To really understand process efficiency, we need to be sure we're comparing the right quantities and are using a meaningful benchmark, or our analysis won't mean very much. As a working example, consider the following steady-state process for producing mechanical work. 1 kilogram per second of water at 20 degrees C is fed to a pump, which produces high-pressure water at 20 degrees C and 20 bar. The high-pressure water is sent to a heat exchanger, where it is heated, boiled, and superheated to 300 degrees C and 20 bar. The steam is then expanded in a steam turbine engine, producing saturated steam plus water with a quality of 95%. This also produces mechanical power, Wt dot, part of which, Wp dot, is used to operate the pump. The boiler is heated using combustion gases, modeled here as nitrogen gas, at 500 degrees C and 1 atmosphere, which exits the boiler at 120 degrees C. We'd like to know three things. How much power does this process produce? How much work is lost by entropy generation in the various units? And, as a basis of comparison, how much work is theoretically achievable from these process inputs? One thing you'll notice right away is that this isn't a heat engine with a high and low temperature reservoir. So the Carnot ratio, 1 minus Tc over Th, even if we could decide what Th and Tc are in this problem, is not really a meaningful benchmark. Also, this process doesn't involve any heat flows in or out of the process, or even among the various units. Although there's thermal energy transfer Q dot Hx inside the heat exchanger as a whole is adiabatic, since if we draw a control volume around it, only material is flowing in and out, not heat. So we need to rethink how we perform a second law analysis for an open system like this. So far we've only considered second law analysis for closed systems, which, to summarize, looks something like this. We place a control volume around a group of molecules, and then examine changes with time in the entropy caused by heat flow across the system boundary at various places, temperatures or times, plus entropy generated inside the system by irreversible processes or steps. For a single group of molecules, this can also be put in intensive form. Combined with the first law, this constraint allows us to solve for various quantities, such as a relationship among state variables when the system transformation is reversible, or the entropy generation when it is not. Recall that by considering both a Lagrangian and an Eulerian control volume around a system, we could recast a closed system energy balance as a much more convenient open system balance involving flows of enthalpy carried by substances across the system boundary. We can do the same for entropy, with the results shown here. Basically, any substance entering or exiting carries with it its own entropy. Meanwhile, we can also have multiple flows of heat in or out at various temperatures along the control volume boundary. Any entropy not attributable to a mass or heat flow must be generated, and this generation must be greater than or equal to 0, according to the second law. Using this form of the second law, combined with the first law for open systems, let's take a detailed look at our process and try to work out the work produced as well as the entropy generation rate in the various units. In order to perform these balances, we'll need some data. First, we'll need to decide on an environmental temperature for benchmarking the value of heat. In the case of a heat engine, we often pick the cold reservoir temperature Tc, since it's usually implied that any heat rejected to the low temperature reservoir has no additional work generating value. But in an open system, we need to establish a common pressure and temperature where all heat and mass flows would end up if we just released everything and let it come to equilibrium with the environment. Since we're in Seattle, let's pick 20 degrees C and 1 atmosphere as our environmental condition. Next, we'll need some enthalpy and entropy data for the H2O in our process. Let's just use the steam table since it has everything we need to know. The other substance we have is nitrogen gas. But it stays at 1 atmosphere, so let's just assume it's an ideal gas, in which case we can calculate the enthalpy and entropy using the ideal gas heat capacity. We can use any reference state we want, but for convenience, let's use the environmental temperature of 20 degrees C, since it may help cancel some terms in our analysis. The ideal gas heat capacity of nitrogen is a 3-term correlation, which we can look up in the back of our textbook. Rather than belabor these calculations, I'll just present the results here for temperatures of 500 degrees C and 120 degrees C, which are the temperatures in streams 5 and 6, respectively. Okay, with those more laborious calculations out of the way, let's take a look at the pump and calculate how much power we're using. Those of you taking Chem E 330 right now might be doing this kind of calculation. But we can also handle it with an open system energy balance. If we assume the pump operates adiabatically, the pump power must balance the change of enthalpy from streams 1 to 2, with a total extensive value proportional to the total mass flow rate, m dot H2O. Since enthalpy at low pressures is independent of pressure, we can just look up H1 in the saturated steam tables at 20 degrees C. But there is no 2 megapascal table for H2O liquid, so we'll need to do that ourselves. If we assume the water is incompressible, delta H will be V delta P, and we can look up mass-specific volume in the steam tables at 20 degrees C. Plugging in numbers, we get 1.9 kilojoules per kilogram of additional enthalpy. Multiplying by the mass flow rate, this corresponds to 1.9 kilowatts of power input. Turning to the second law, and assuming the pump is adiabatic, we can solve for the net rate of entropy production, S gen dot. But since water is incompressible, we expect S1 and S2 to be equal, with a value given by a saturated H2O liquid at 20 degrees C. Thus, S gen dot is 0. This also means that work lost by the pump, T naught times S gen dot, is also 0. Moving on to the turbine engine, if we again assume adiabatic operation, the power produced will be the mass flow rate times the difference in enthalpy between streams 3 and 4. Stream 3 we can just look up directly in the steam tables. The enthalpy of stream 4 will be a quality weighted average of the saturated gas and liquid enthalpies at 1 atmosphere and 100 degrees C. Taking the difference, we get 460 kilowatts of power. Deducting the 2 kilowatts required by the pump, this means a net output of 458 kilowatts. Examining the second law, the formulation is similar to what we had with the pump. In this case, S gen dot is proportional to the mass flow rate times S4 minus S3. Looking up entropy values in the steam tables and taking another quality weighted average for stream 4, we get the values shown here. The difference corresponds to a net entropy generation rate of 0.287 kilojoules per Kelvin per second. Multiplying by the environmental temperature T0 of 293 Kelvin, we obtain 84 kilowatts of lost work. So it appears our turbine engine is not 100% efficient. Okay, so now let's look at the heat exchanger. The issue we need to address here is how much hot nitrogen gas we need to heat and boil the H2O under the conditions outlined in the process. For convenience, let's place the control volume around the whole unit, in which case we don't need to think about the heat passed from the hot side to the cold side. We can just treat it as an adiabatic unit with streams entering and exiting. So according to the first law, the molar flows of gas will be tied to the mass flows of H2O. Solving for the molar flow rate of N2, it is proportional to the water mass flow rate times the ratio of the enthalpy changes of H2O versus N2 across the heat exchanger. Plugging in numbers from the steam tables and our previous calculations, we get a nitrogen flow rate of 255 moles per second. Note that a heat exchanger does not consume or produce any work, but can it lose work? Let's take a look by calculating the entropy generation in the heat exchanger. Applying the second law and again assuming adiabatic operation, Sgen dot will be the sum of the entropy increase of the water plus the entropy decrease of the nitrogen. Plugging in numbers, we get a non-zero positive value of 1.257 kilojoules per Kelvin per second, which after multiplication by T0 corresponds to 368 kilowatts of lost work, a much larger loss than the turbine engine. So although the heat exchanger is not a work-producing or consuming unit, it can still lose work. This can be understood by comparing to the Stirling engine, where we traced all entropy generation to temperature gradients. Looking here, we have a massive temperature gradient from 500 degrees C nitrogen to 300 degrees C H2O. So inside the heat exchanger, we're making lots of entropy, and this reduces the amount of work we can recover elsewhere in the process. Summarizing, we found we are producing 458 kilowatts of net power. Although the pump loses negligible amounts of work, the heat exchanger and turbine together lose nearly as much work as we're producing. So what does that mean exactly? On the face of it, that sounds like it might be 50% efficiency. But this assumes we've already identified all the relevant sources and fates of work in our process. But have we? The problem is that so far we've only answered 2 of the 3 questions we originally outlined when we started this example. We know how much work we're producing, and we know how much work we're losing in each process step. But what is our benchmark for the total amount of theoretically recoverable work? And how much theoretically recoverable work are we wasting in the exit streams? Without this information, it's hard to put the numbers we have here in perspective. So what do we mean by the theoretically recoverable work? Recall that for a heat engine, there's a limit to the amount of work we can collect as heat flows from the high temperature reservoir to the low temperature reservoir. This is given by the Carnot ratio. But in our process here, we don't have reservoirs. We don't even have heat flows into or out of the process. Thus, we need to somehow generalize this idea for other sources besides heat. In particular, imagine we have a more general source, comprised of one or more substances that are out of equilibrium with the environment. They can be out of equilibrium in many different ways. They can be at a higher or lower temperature. They can be at a higher or lower pressure. They can be unreacted substances like air and fuel that, given the opportunity, will react to release energy in the form of heat or work. Or they can be any combination of these things. But whatever state they're in, given some mechanism, these substances will want to relax to equilibrium with the environment by evolving or absorbing heat, expanding or contracting or reacting to form new compounds. Once they reach equilibrium with the environment, we can no longer extract any useful work from them, much like the heat rejected by the heat engine to the cold temperature reservoir. We call this state of equilibrium the environmental ground state. In reaching equilibrium with the environment, the substances comprising our source will also, in general, release a certain amount of heat, Q dot, which also ends up as thermal energy in the environment. The question we need to address is how much work could we theoretically obtain from our source if we allow it to relax completely to equilibrium with the environment through a 100% reversible process with zero entropy generation. As we saw with the heat engine, this condition corresponds to the maximum work we could possibly obtain, or conversely, the minimum work required to return substances in the environmental ground state back up to the state of our source. This reversible work, Wrev, must also in general be accompanied by a certain amount of reversible heat, Qrev, which must pass to or from the environment in a state of equilibrium at temperature T0. Although it sounds like a complicated question, it's really not. If we draw a control volume around our entire process and treat the source, exhaust, heat, and work as continuous flows at steady state, we can express the first and second laws as open system balances. According to the first law, Qrev plus Wrev must equal the sum of n dot times H for the source substances entering the process, minus the sum of n dot times H0 for the substances rejected to the environment, where H0 is the enthalpy of the rejected substances in their environmental ground state. Likewise, according to the second law, with Sgen equals 0, Qrev over T0 will be equal to the sum of n dot times S for the source substances entering the process, minus the sum of n dot times S0 for the substances rejected to the environment, where S0 is the entropy of the rejected substances in their environmental ground state. Solving for Wrev, we find that the net reversible work will be given by the sum of n dot times H minus T0S for each substance entering the process, minus the sum of n dot times H0 minus T0S0 for each substance rejected to its environmental ground state. In process efficiency analysis, this maximum amount of reversible work that can be obtained from a source or stream is called the exthalpy of that source. Exthalpy has a few other equivalent names, including availability and flow exergy. These are the same thing. The use of exthalpies to analyze efficiency of a process is often called availability analysis or exergy analysis, but really these are just fancy terms for process efficiency analysis. Armed with this idea, let's take a look at the exthalpy of the streams entering our process. H2O and N2 enter in streams 1 and 5. If we imagine relaxing these streams reversibly to the environment, their exiting ground states would be liquid H2O and gaseous nitrogen at 20 degrees C and 1 atmosphere. Since the water enters in stream 1 as a liquid at 20 degrees C and 1 atmosphere, it's already in its environmental ground state, so contributes nothing to the incoming exthalpy. Also, since we chose a reference state for H and S for nitrogen to be the environmental ground state, we are left with only two terms involving H5 and S5. Plugging in numbers, it implies that the nitrogen entering our process has the potential to do over 1,500 kilowatts of work. So far, we've only accounted for about 900 kilowatts of net and lost work. So where's the rest? To answer that, let's also look at the exthalpy of the process outputs in streams 4 and 6. Collecting terms, and once again recognizing H0 and S0 for nitrogen are both 0, we get the expression shown here. Plugging in numbers again, we find the nitrogen and steam leaving the process carries with them 600 kilowatts of unrecovered work potential. That's a greater loss than the entropy generation in all of our equipment combined. Our results are summarized here. Out of a possible 1,500 kilowatts of theoretically available work, we only collect about 30% of it. Of the 70% we don't recover, 40% exits as exthalpy in the exhaust. Unless we do something else with those streams, this should be considered a loss. As for the process itself, the largest irreversibilities are in the heat exchanger, which has large temperature gradients and thus generates a lot of entropy. Thus, if we wanted to improve this process, the first priority would be examining ways we could recover more work from the exhaust. Second priority would be improving our heat exchanger. The turbine engine, with only 5% loss of recoverable work, is the least of our worries. To take this one step further, we should probably recognize that the high-temperature nitrogen stream we've been considering is just a model for the combustion exhaust of a fuel. If we take a step back and consider the combustion as well, our process actually looks more like this. Here a stream of methane reacts with excess air to produce high-temperature exhaust containing mostly nitrogen, but also excess oxygen, CO2, and H2O gas. How does our process efficiency analysis change if we include the combustor as part of the process? Since we now have a lot more compounds as well as a reaction, it's getting a bit complicated to solve this problem by hand. So let's switch to an Excel spreadsheet model. Here on the left we have a data block that includes the heat capacity and other thermodynamic parameters for calculating enthalpy and entropy of the various species in the feed and exhaust. Since we have a reaction, we need to include the enthalpies and entropies of formation for all the non-elemental compounds, including methane, CO2, and H2O, as well as the enthalpy of vaporization for H2O. For convenience, I've adopted a reference date of 20 degrees C, interpolating the barren thermochemical tables for enthalpies and entropies of formation. We'll discuss this database in more detail toward the end of the quarter. Below that is a small process parameter block with stream temperatures and flow rates. The values marked in red are the variables we must solve iteratively using material and energy balances. These include the total airflow rate in moles per second and the methane to air ratio in the feed to the combustor. Over here on the right, we have an enthalpy table for solving the mass and energy balances on the combustor. This problem is very similar to an adiabatic flame temperature calculation, which you probably did at least once in Chem E 310. The purpose of the table is to organize the molar flows and molar enthalpies of each species in adjacent columns so that we can multiply them together in a third column and then add up the rows to get the total convection of enthalpy into the combustor. Likewise for the substances exiting the combustor. At the same time, we also solve the molar balances taking into consideration the disappearance of methane and oxygen and the formation of CO2 and water. Since in this case we have specified the inlet and outlet temperatures of the combustor, we can directly calculate all the molar enthalpies and then just adjust the methane to air ratio until the energy balance is obeyed. Moving down, we can likewise use an enthalpy table for solving the energy balance on the heat exchanger. Since this unit is also adiabatic, what we're doing here is specifying all the inlet and outlet temperatures and then adjusting the total airflow until the energy balance is obeyed. With all the flows established, we can then do a second law analysis on the combustor and heat exchanger to determine the entropy generation and lost work in those units. Like enthalpy, this is also very conveniently accomplished using a table where we can multiply n dot times the molar entropy for each species and then add up the species to get the total convection of entropy in or out of each unit. This difference in total entropy convection in and out is the entropy generation rate, since the units are both adiabatic. The turbine we calculated by hand already, with the results repeated here. Finally, the exthalpy of the inlet and outlets can be determined by summing H minus T0S for each species and then subtracting the sum of H0 minus T0S0 for the species in their environmental ground state. Note that because there is a reaction, the species entering the ground state, including CO2 and H2O, are different than the species in the feed, methane and O2. Thus, it's not really possible to calculate the exthalpy of individual species and add them up. Exthalpy is more of a collective property of a stream or group of streams. A summary of the results is shown here. As you can see, with the combustor included in our considerations, the picture changes quite dramatically. If we consider the source to be fuel and air, the maximum reversible work is over 3,600 kilowatts, of which we're only recovering about 13%. The step of combustion to a final temperature of 500 degrees C involves an enormous loss of work, over 2,100 kilowatts, almost 60% of the work potential of the fuel and air. This trumps all the other losses in our process combined. So if we really want to improve things, finding a way to mitigate entropy generation associated with unrestrained combustion should feature very heavily in our priorities. One way workers have sought to address the efficiencies described here is using something called a gas turbine combined cycle. Rather than just combust fuel to make hot gases and then boil water at a low temperature with it, a gas turbine engine pressurizes air to high pressures and temperatures where combustion results in much less entropy generation. This energy of combustion is captured at high temperatures in a gas turbine engine, which produces exhaust at 400 to 500 C, the starting point of the process we analyzed previously. By using this exhaust to boil water in a heat recovery steam generator and running a second steam cycle, the overall exergetic efficiency can be as high as 60% or higher. Another way to avoid the irreversibility of combustion is to use fuel cells, which force combustion reactions to occur near equilibrium under the control of an electrochemical potential. Fuel cells can be combined with advanced turbine cycles like the one shown here to obtain extremely high overall efficiencies that can extract most of the available exthalpy from a fuel source. If these are issues you find interesting, the departments of Chemical and Mechanical Engineering at UW offer several upper division electives in process efficiency analysis and advanced energy conversion systems. Unfortunately, that's all the time we have in this course to spend on it.